So in order to, as we said, give some examples of how different complexity classes work, we are going to be focusing in sorting algorithms. And the first, let's say, a bit more interesting class that we saw last time, with that algorithm about counting repeat occurrences of elements in one list, was the O to the n squared complexity class. So quadratic complexity. So naturally, we're going to start with some simple sorting algorithms, and very specifically with insertion sort, which is a simple and, because of that, not very fast, as we will see, sorting algorithm. How does it work? It works the following way. We are always going to have, in all the execution of this algorithm, two parts in our list of integers that we want to sort. The first part is going to be the part of the list that's already sorted. Okay. First part, elements that I have already sorted. And the second part is going to be, well, naturally, the part of the list, the elements that I have not sorted yet. I'm going to iterate over all the list. At first, the part of the list that I have already sorted is going to be very small. I'm going to consider that only the first element is already sorted. It's one element, so it is sorted by default. And then I'm going to iterate. I'm going to go over all the elements in the list, and I'm going to make it so the part of my list that is sorted grows one element with each passing iteration. How am I going to manage that? Well, every time I reach a new element, I'm going to search for the place in the sorted part of the list, so in the first part of the list, where this element, that I'm going to call current, should be placed. So I'm going to have my sorted part of the list and the unsorted part. I'm going to take the first element in the unsorted part, and I'm going to call it current. And then I'm going to insert it in the sorted part of the list where it should go. And this is the place of the sorted part of the list where the elements stop being smaller than current. We will name this position pose, and we will keep track of this position. And then what we are going to do is we are going to shift all the elements that are bigger than current one position to the right and put current in its correct position. Something like this. As I was saying, I'm going to start in the second position because I'm going to consider the element in the first position as being sorted. One list elements are sorted. And then I'm going to choose a current. I'm going to be choosing it iteratively, always one more position at a time. And I'm going to find the position where it should go. I'm going to suppose it's in the right position at first, and then I'm going to move the elements that are larger than it in the sorted part of the list to the right. And every time I'm doing that, I'm going to note that my element, my current element, is not in its right position, but should be one position to the left. So when I finish this while loop, all my elements that are bigger than current will have moved one to the right, and current will have jumped as many times as I need to the left and will be in its correct position. Okay? We can run this here. I'm going to actually not run that version, but one that is a little bit, let's say, more verbose. I'm going to add some print statements here, some calls to the print function, so that I know what I'm going to do at each step. This is a very common way of following how a piece of code is running. It's also used for debugging to find where my errors are in my code. and I'm going to use it to illustrate a little bit how my algorithm works. Okay, and I'm not going to run this at this very moment. Well, I'm going to run this, but not this one. I'm just going to show you a previous execution that I did, and I generated a random list, this one. Okay, and I did all of the steps. I always have a sorted part. At the beginning is just one element, and an unsorted part that contains more elements, and I go growing the sorted part and making the unsorted part smaller until all my list is sorted. Okay, but let's see this with a little bit more detail. You can follow it here in the text, and I have prepared a little bit some slides so that we can see it a little bit better. See, this is the same list that I had before: 3, 10, 7, 2, 5, 1. Okay, so let me just begin running insertion sort. What do I do? Well, first of all, as I was saying, I consider a sorted and unsorted part of my list. At the beginning, as we were seeing before, the sorted part of my list contains only one element. Okay, here for I in range. Okay, this contains just one element. I can see that here because my loop starts at 1. So I can say that when I begin the execution of my algorithm, the sorted part of my list contains exactly one element, 3 in this case, and the unsorted part of my list contains all the other elements. Well, I seem to be getting some acting up from my Bluetooth mouse at this moment. Let's not worry too much about it. As I was saying, at the beginning, I have one element in my sorted part and the rest of elements in the unsorted part. And let's see what happens next. In the second step, what would be, let's see, value I equals 2, I get this. I get that current is here in this position 1 and with element 10. Okay, so I in this case is 1, I'm in position 1, and my current element is 10. And what I have to do is insert 10 in the correct position of the sorted part of the list. And I'm hoping that the sorted part of the list will now become the two first elements. So far it's the first one, and I'm going to hope that I can make the two first elements in the list, the two initial elements in the list, the sorted part of the list. And in this case, I don't need to do much because 3 is smaller than 10, so I'm already where I should be. It doesn't need to move. This part of the list is sorted. Okay, not so fast. Next iteration, what do I do? Well, I move the current element pointer, and now I equals 2, and I'm at the third element in the list, 7 in this case. What do I do? Why do I need to do now? I need to insert 7 in its correct position in the sorted part of the list. And 7 is bigger than 3, but it's smaller than 10, so it should go here. So what I'm going to do is check how many elements are smaller than 7,